Hello, my dear students. Today I will be discussing on Unit 4. It has chapters like thick and thin cylinders, springs, columns, and struts. First, I will start with the cylinders. Okay. In engineering field, we daily come across vessels of cylindrical and spherical shapes containing fluids such as tanks, boilers, compressed air receivers, etc. Generally, the walls of such vessels are very thin as compared to their diameters. These vessels, when empty, are subjected to atmospheric pressure internally as well as externally. In such a case, the resultant pressure on the walls of the shell is zero. But whenever a vessel is subjected to internal pressure due to steam or a compressed air, etc., its walls are subjected to tensile stresses. In order to meet with several requirements, the fluids are stored under pressure in pressure vessels or shells or cylinders and transmitted from one place to the other through pipes. Pressure vessels are made of cast iron, steel and non-ferrous alloys. Special material is used for chemical vessels. Vessels of spherical and cylindrical form are used for storing fluids under pressure. For example, steam boilers, air compressors, tanks and water tanks. Spheres are used for containing gas under pressure. Liquid and gases causing internal pressure in a closed vessel are referred as fluids. When it is a gas, the pressure is constant in all the parts of the vessel. In case of liquid, the pressure is lowest at the top and increases with depth. When the vessels are empty, I already told, it is subjected to an atmospheric pressure both internally and externally, and hence the resultant effect of atmospheric pressure is nil. Okay, when the cylinder is subjected to internal pressure at any point on the cylinder wall, three types of stresses are induced on three mutually perpendicular planes. That is, the first one is hoop stress or circumferential stress. The stress acting along the circumference of the cylinder is called circumferential stresses. This is directed along the tangent to the circumference and tensile in nature. Thus, there will be increase in the diameter. This circumferential stress is represented by sigma c. Okay. The second one is longitudinal stress. The stress acting along the length of the cylinder, that is in the longitudinal direction, is known as longitudinal stress. This stress is directed along the length of the cylinder. Here, this is also tensile in nature and tends to increase the length. The third one is radial pressure or radial stress, represented by P. PR. It is compressive in nature. Its magnitude is equal to fluid pressure on the inside wall and 0 on the outer wall if it is open to atmosphere. You can see here, this is hoop stress. The stresses are developed across the circumference of the cylinder. This is a longitudinal stress, that is here this is stresses are acting along the length of the cylinder, and radial stress, it is acting along the radius of the cylinder. Okay, this you can see here how the stresses are induced. These are the stresses are induced like this direction. Okay, circumferential is represented by sigma c, and longitudinal stresses along the length, so it is represented by sigma l, and this is along the circumference or radial, so that is radial stress is represented by PR. Okay, this is an element on the cylinder wall subjected to these three stresses. So this cylinder is subjected to all these types of stresses. Okay, now we'll see what is these cylinders. Okay, a cylindrical vessel or shell may be thin or thick depending upon the thickness of the plate in relation to the internal diameter of the cylinder. Here, a cylinder or a spherical shell is considered to be thin when the metal thickness is small compared to internal diameter. Its thickness is very small when compared to the diameter. That is when the wall thickness T is equal to or less than D divided by 20, where D is the internal diameter of the cylinder of the shell. Means here the thickness is equal to or less than 1 divided by 20 times of the diameter. Okay, so then you can say this is thin cylinders. Okay, and here the magnitude of radial pressure is very small compared to other two stresses in case of thin cylinders, and hence it is neglected. Here radial pressure is very small here compared to the other two stresses. Other two stresses are circumferential stresses and longitudinal stresses, but radial stress is very less, so it is neglected in the case of thin cylinders. Thus, a thin pressure vessel is one whose thickness is the thickness to inner radius ratio is not greater than 1 divided by 10. And in thin cylinders, the stress may be assumed uniformly distributed over the wall thickness. For example, boilers, tanks, steam pipes, water pipes, etc. are the examples. Thin cylinders are frequently required to operate under pressure up to 30 meganewton per meter square. So, it has the capacity of a pressure up to 30 meganewton per meter square. Okay, and here generally, in case of thin cylinders, the walls of the vessels are very thin as compared to their diameters. These vessels, when empty, are subjected to atmospheric pressure internally as well as externally. In such a case, the resultant pressure on the walls of the shell is zero. But whenever the vessel is subjected to internal pressure due to steam or compressed air, its walls are subjected to tensile stresses. You understood, I think. If it is empty, there will not be any stresses. Like it is subjected to atmospheric pressure internally and externally, but the resultant pressure on the walls of the shell is zero. But when it is full, whenever the vessel is subjected to internal pressure, is if it has steam or a compressed air, its walls are subjected to tensile stresses. Now we'll see what are the different failures of thin cylindrical shell due to internal pressure. Okay, whenever a cylindrical shell is subjected to an internal pressure, its walls are subjected to tensile stresses. Means when the cylinder is subjected to some pressure, its walls are subjected to the stresses. That stresses are tensile stresses. If the stresses exceed the permissible limit, the cylinder is likely to fail in any one of the following two ways. Like the cylinder has certain capacity, so it resists or it permits only that limit. But if what happens, if the stresses exceed the permissible limit, the cylinder is likely to fail. Means it may burst. Right? In any one of the following tools, there are two ways of failures. The first one is it may split up into two troughs, or it may be split up into two cylinders like this. It may be split up into two troughs like this. It may split, or it may split into two cylinders. Okay, there are two ways of failure of thin cylinders. Okay, the first one is split into two troughs, and second one is split into two cylinders. Now first we'll see what are the stresses in the thin cylindrical shell. We know that whenever the cylindrical shell is subjected to internal pressure, its walls are subjected to tensile stresses. The walls of the cylindrical shell will be subjected to the following two types of tensile stresses. There are two types of tensile stresses. When the cylindrical shell is subjected to pressure, internal pressure, if the walls are subjected to tensile stresses. So there are two types of tensile stresses. The first one is circumferential stress and second one is longitudinal stress. The radial stress is neglected because it is very small in case of thin cylindrical shell. In the case of thin shells, the stresses are assumed to be uniformly distributed throughout the wall thickness. Okay, here it is assumed that the stresses are uniformly distributed throughout the wall thickness. However, in case of thick shells, the stresses are no longer uniformly distributed. So, the problem becomes complex in the case of thick cylinders. Now we will see how to find the circumferential stress. Okay, let us consider a thin cylindrical shell subjected to an internal pressure as shown in the figure. Okay, and we know that as a result of the internal pressure, the cylinder has a tendency to split into two troughs. I have told there are two types of failures. It may be split into two troughs or it may be split into two cylinders. First, we will take this condition. First condition, it may be split into the two troughs. Okay, like this. It may be split into two troughs here. So here L is the length of the shell and D is the diameter. This D is the diameter and T is the thickness of the shell and P is the internal pressure. What happened here? You have to calculate the total pressure. What is total pressure here? Here you can see the stresses are developed along the circumference of the cylinder. Okay, here the stresses are developed in the x direction. This is the diameter and this is the stresses. This is T is the thickness. Now total pressure is equal to intensity of internal pressure into area. This is total pressure. Okay, total pressure is given by intensity of internal pressure into area. What is intensity of internal pressure? That is P into area is D into L. Okay, that is the area of the this one cylinder trough. It is divided split into two troughs, so that is P into D into L. Now you have to calculate what is circumferential stress in the shell. What is circumferential stress? That is given by sigma C is equal to total pressure divided by resisting section or resisting pressure. What is the total pressure? That you have calculated here, P into D into L. Resisting section means it is the resisting force to the this pressure developed. So that is it is cut into two troughs. So 2 into thickness into length area. Okay, resisting force is 2 into T into L. Simplify this L get cancelled, so PD divided by 2T. Okay, this 2 is because of two section. Now this is a tensile stress across the XX direction and it is also known as hoop stress. Suppose if there is this nu is the efficiency of the riveted joints of the shell, then the stress is given by this formula PD divided by 2T into efficiency. Okay, nu. So this is the formula to find the circumferential stress. You just remember this how you will get this circumferential stress, that is PD divided by 2T. Once if you know that if there is some means efficiency means suppose if it is while jointing there may be some loss of this pressure. Okay, in such a cases you have to consider what is the efficiency of that. So that is given by sigma C is equal to PD divided by 2 into T into efficiency. Maybe it may be 70%, maybe 20 or 30% there may be a loss. So that is the efficiency. So this is the way to calculate circumferential stress. In the next class, we'll discuss how to calculate longitudinal stress. I hope all of you understood. Thank you.